All right, let's have fun going over rotational energy and angular momentum homework. So I think there's 10 problems, each, not all of them, but some of them have their own parts. So this is probably going to be extended over at least 2 tutorials. It's really important that you look back at your notes and the examples done to help you understand this. Don't rely solely on what I'm about to tell you because you didn't put the effort in to work through as much as you possibly can. I understand that a good amount of this might be confusing to you, but you have to be able to work through it yourself. The last resort is relying on me to tell you how to do it. Okay, with that in mind, let's do our best. So number one is very, very similar to the problem that you had from the note sheet. The only difference here is that you have a hollow sphere and not a solid sphere. So the analysis is pretty much the same. You basically have UG, so I'm just going to jump right into it. MGH goes into 1/2 mv squared plus 1/2 I omega squared. Well, I is 2/3 m, okay, r squared. And then omega squared is just v over r quantity squared. So I'm just doing that all in one step. The m's cancel out. And then I'm just going to work on the right side here. This is 1/2 v squared. And this term right here from the 1/2 I omega squared reduces to 1/3 v squared. All right, shouldn't be too hard to show why that is. So I combine both those terms and I get 5/6 v squared. Now, remember, that's equal to GH, so I want to know V, and V turns out to be equal to 6/5 GH, and if you plug it in numbers, you get the answer that was given. Okay, so this is the second time through this type of problem, and you hopefully see it's pretty straightforward. Now, this is a little bit different. Develop an equation for angular momentum in terms of m, r, and the height dropped. So as it rolls down, it's going to spin faster and faster, and it's going to have angular momentum at the bottom. Now, we also know the velocity at the bottom, and that's at least an equation for that. So that's going to be really helpful because velocity can be translated to omega. And when you see omega and you want to relate it to L, what you want to think about is I omega. There's no conservation of angular momentum here because there is an external torque to the object itself. It's coming from the ramp. So we can't use a conservation one here. So if I do I omega, well, we already know that I is 2/3 mr squared, and omega is going to be v over r. I keep switching back and forth. Now, v we found to be radical 6/5 GH from above. Okay, so that makes this a little bit of a pain. So this let's cross out this r. So we got 2/3 mr, and then for this r is canceled out. But for the v, we're going to put in 6/5 GH. Doesn't look like there's a ton that we can do with that, but if you plug in the values, you should get a point for your calculation. Okay, C. All right, now we want to express rotational kinetic energy in terms of angular momentum while it's rolling, and then apply it to the hollow sphere. Okay, so this or I'm hoping it reminds you of something we did before when we were looking at kinetic energy and linear momentum, right? Ke translational and P. We developed an equation, I'm just going to write over here, where Ke was P squared over 2m. Well, we could express this in terms of rotational we can express in terms of translational, linear momentum we can express in terms of angular momentum, and do it all. But I think the easiest way is just take these parts and realize that wherever there is a translational, we can just transcribe a rotational. So we can say rotational kinetic energy, the 1/2 is going to stay the same. And instead of P, we're going to put an L squared, and instead of M, I think you can guess it's going to be, that's right, I. Okay, so the moment of inertia. So that's a handy equation that you can fairly easily derive. So for the hollow sphere, that translates then to 1/2 L squared over I, okay? And that then becomes 1/2 L squared, and I is, again, 2/3 mr squared, so 2/3 mr squared. And 1 divided by 2/3 is 3/2. 3/2 times 1/2 is 3/4. So that becomes 3/4 L squared over mr squared. Okay, so that's not too bad. All right, now we can use all these relationships to do some general proportion stuff. Stuff you guys love to do. So I've got two solid spheres. So that's good. They have the same moment, right? From the same height, same time. Sphere A, so what's the difference? Twice the mass and twice the radius as B. At the bottom, we can ask the ratio of B to A for the following when we want to show equations, okay? So we want to know how fast you're moving in terms of linear speed. Well, what's our equation for linear speed? Well, we know we have an equation for speed for above. Well, it actually doesn't matter. We could go back to our notes, but when you looked at our equations for linear speed at the bottom, we know it was basically equal to some constant, or a square root of some constant times GH. In other words, it didn't matter what M was or R was, so it's simply going to be 1-to-1, right? So V, I'm not going to write the subscripts, I'm just going to put 1-to-1 there. So we want you to understand conceptually, in other words, we want to rederive all these equations, that the linear speed doesn't depend on mass or the size of the object. Okay, angular speed is a little bit different, right? Because we know that angular speed is V over R, so there is an R term in there. So in other words, we could say omega B over omega A is, ignore the V part because the V is the same for both, so it's proportional 1 over R. So that's, if you do the math, I'm not going to go through all that. That's going to be RA over RB, right? In other words, 1 over RB divided by 1 over RA is RA over RB. So what's the difference between A? A has twice the mass, so that's going to be 2-to-1. So omega B, or excuse me, B is going to have a faster angular speed, twice as much. How can it have the same linear speed? Well, it's offset by its smaller radius. Okay, angular momentum. Well, angular momentum is most easily calculated as I omega, right? Okay, I is the same, so omega is different for both of those. Wait, I'll take that back. I was wrong. I is not going to be the same. Erase that because they are different M's and different R's. So we're going to have to do a little calculation. I'm going to do it up here. What is I of A? It's its mass, 2M times 2R quantity squared, which is 8mr squared. Okay, so IB is just going to be mr squared. So in terms of angular momentum, LA is 8mr squared times a regular omega, and B is mr squared, and it has twice the omega. We established that before, so we can see that B over A, this is 2, this is 8, so it's 1-to-4. Okay, sorry about that little goof up with moment of inertia. And then lastly, kinetic energy of one versus the other. Okay, well, let's look at in terms of I omega squared, right? So that's I omega squared is a 1/2 in there, but the 1/2 is common to both. So it's kind of similar to D. We're going to have, for A, we've got 8 omega R squared times a regular omega, so that's just 1 squared. And for B, it's mr squared. and it has twice 2 squared, so that's 4 over 8. So the kinetic energies A to B, or excuse me, B to A is 2 to 1. All right, so it's a little bit of a pain to work out, but do the algebra yourself. Okay, number 2, completely different problem. If there was a great migration of all the peoples and cats, can't forget about the cats, of the Earth towards the equator, would it affect the length of our day? Now, what kind of question is that? All right, so there's good old planet Earth, there's the equator, there's the axis about which we rotate. So if everything starts moving, right, that way, why would that affect the length of our day? Well, the length of our day is based on, right, time of a day is based on angular velocity. And what does angular velocity depend on? Well, it depends on angular momentum. So basically what this problem translates to is, will the Earth's angular momentum change or anything else thereof? Well, no. L prime equals L because no external force, or excuse me, external torque. Okay, that's super important. Because everything's on the Earth, there's nothing external to the Earth slash people, cats, that's going to change that. So the next question is, well, we got to be careful. Well, we can't just automatically say omega is going to stay the same because L prime is equal to I prime, omega prime, and we're looking at whether omega prime changes. Well, does the moment of inertia change? And the answer is I prime will, well, what will it do? Are we getting closer or further from our axis of rotation? Well, if you go to the equator is about as far away from the axis of rotation as you can be. At the poles, you're right at the axis. So I will increase. We're putting more mass far away from that. Therefore, omega prime will decrease. That's crazy. So moving everything towards the center of the Earth will slow down the Earth because we have to conserve angular momentum. Who would have expected that? Okay, let's try to do one more problem before my 15 minutes are up. Estimate the angular momentum of the Earth as it orbits the Sun. You're given mass and blah and a blah. So how do we do that? Good question. Okay, so what equation are we going to use for that? Well, we want angular momentum, right? We could use I omega. Okay, but the problem with that is we don't really have, well, we could do the moment of the Earth based on the fact that it's a solid sphere. Okay. We're going to actually do it a different way. We're going to take the fact that the Earth has a mass. Okay. Oh, I'm sorry. I'm completely got the wrong problem. Okay, let me start that again. I was thinking of a rotating Earth. I did not read the problem carefully. So we have the Sun. We're going around and around that. So we are a certain distance away, r. We're moving with a certain v at any given point, tangent to that. So the angular momentum is just going to be mv cross r. Okay, so you should be able to put it in numbers and get the answer of a very large number, something times 10 to the 40th. Now, the v wasn't given, so let me be clear. How do we get v of the Earth in a given instant? Well, 2 pi r all over t, right? It's simply the circumference divided by the time. So that's where the period comes into play. All right, I'll let you work that out. You should be fine. All right, I'll stop there, and we'll pick up for tutorial 2 for number 4 on.